Okay guys, so we did with the state feedback control law when that you wanted to push your system, any system, to the origin, that's right. But in the reality, so we want to push the temperature room to 75 Fahrenheit, or when you're using the cruise of your car system, so you want to keep the speed of your car to, I don't know, 65 miles per hour, or too many things, that's right. So that's why here I'm going to teach you by analytically and the Matlab controller design when the plant or system has an integrator integrator. I'm underlining why, because if you remember that when your system has integrator, so why we are using the I in PID, because when you add I, the error signal goes to 0. Remember, when time goes to infinity, you don't have error signal. Remember undergraduate control? If you don't know, I'm teaching you. So with non-zero or not origin, 0 reference input. So this is fundamentally different from the state feedback that I taught you in the previous classes. So here is saying that the plant has integrator in the transfer function and with non-zero reference input. Okay, so again, we are dealing with the LTI system. X dot is equal to AX plus BU. If your system is linear, that's fine. If it's non-linear, you can linearize around the equilibrium point of the system. And assuming that for this example, specific example, assuming the reference input, okay, R of t, this is that you want to follow, this is desirable, you want to follow this, can be, I don't know, 75 Fahrenheit as a temperature room, is a step function. I'm gonna do by Matlab, by coding, okay? So for this system, now you have to revise the state feedback control law. The state feedback control is gonna be U, gonna be minus, U gonna be, gonna be minus 0, K2, K3, Kn for the nth order system. And these are your state variables, x1, x2, xn, that's right, plus this, you see that I made it 0, I just moved it here. K1 is here, so K1 in R minus x1, that's right. So this is how we define the state feedback control law when your system has an integrator and you are following a step function. Understand? So on the other hand, if you return it back here, this K1 x1 here, you're gonna have this, that's right, look at here, you're gonna have K1, K2, K3, Kn, right, in x1 to xn, that's right, plus K1R. So if you lump that, you're gonna have gain matrix X plus K1R. So we know that now. This is your feedback control law. Bear with me. And this K1 is the first element of your gain matrix that you are already how to know it by Ackermann formula. That's right. I will teach you by an example. Okay. So now let me implement this analytically inside this LTI system. So if I do that, we do some math, then I will go to Matlab. So because the system is x dot is equal to ax plus bu, and we said that the ax plus b, your u is minus gain x plus k1 r. That's right. So I'm factoring out x. So what you're gonna have again is a minus bk minus bk, as we have seen previously, and the remaining is gonna be what? The remaining gonna be plus b k1 r, right? Equation number 1. Why I'm doing that? Because I want to see, as you remember, undergraduate control, you had two terms. One of them was transient response, transient, even the vibration course, transient response. That's right. And we had steady state response, steady state response, remember? A and B. But at the end of the day, in the system that you are controlling, you want to see that what's the steady state response of that. After some oscillations or transient response, look at here for remind you from the undergraduate control. Suppose that here's a step input that you want to follow. So here was like this, right? So we name here from undergraduate control, if you remember it, this is the transient response that is vanishing after a certain time, that the time was settling time, remember, settling time. But this is the steady state response. So this is very important. For example, if you want to keep the room temperature to 75 degrees, so you're going to have these responses, right? Because in the room temperature control problem, you don't want to have the oscillation overshoot. So you make your problem as a, because it's first order dynamical system. So you have, this is your transient and this is your 75 degree. Understand? Suppose here's temperature. Suppose here's temperature. Understand? So the same here is valid. So if you want to do that, I want to see what is x dot at time infinity. At time infinity, I'm just putting here. So going to be a minus bk x at time infinity plus b k1 r as time infinity. I'm naming equation number 2. But I told you that the reference input is r, the step input. See? This is the desirable things that you want to follow. So for example, 75 degree. You want to make the temperature of the room this value. And here is T, that's right, this value. So R at infinity is again is equal to R, that's right. Oops. What's happening? That's right. Okay. R is at, so this at the end of the day, it's gonna be R because R is constant. That's right, huh? So what I'm gonna do, I'm gonna subtract 2 from 1, equation number 2 from 1. So you're gonna have x dot minus x dot at time infinity, steady state, means steady state at time infinity, is equal to a minus bk at x of t minus x at time infinity. That's right, x minus x infinity plus bk1 r minus r at time infinity. But we know r at time infinity is r, so this goes to 0, right? So what you get is x dot is minus steady state value gonna be a minus bk in x minus x infinity. So we know that from undergraduate control and even here This value is how much? The error signal. That's right. Because suppose that when you have this profile for the temperature of this room, at this, here is no, let me do this. If I do this, okay, then this is transient, this is steady state. So this value gonna be x minus x infinity. This is x infinity, this, and this is x off on that second. So you have an error signal here, that's right. So if that error signal is gonna be E dot is equal to A minus BK in E, right? So, and we know that by selecting or tuning the proper K, the eigenvalues of this E gonna be negative, so E goes to 0. You see that based on whatever I taught, this state control law gonna stabilize system and push it to non-zero reference if your system has an integrator. Okay, so if I want to summarize, if I want to summarize, first let me write it here. Let me write equation number 2 here. Equation number 2, this. So what you're gonna have is that x dot at time infinity is equal to, I'm leaving blank because I want to write something, A minus BK, this is the game metrics that you're gonna design, x at time infinity plus BK1R. Now you let me know, what is x dot at time infinity? Here we go, look at it. Do you see any change? No. So x dot gonna be how much? 0. That's right. So from here you can understand that the steady state value of the x gonna be minus A minus BK inverse multiplying the both sides in BK1R. That's right. On the other hand, just look at here. Your x at time infinity goes to how much? These are the gains. That's right. Goes to R. And u at time infinity, based on whatever I defined, gonna be minus k x at time infinity, kx at time infinity, plus k1r. See here, we just did it. So what is x at time infinity? Is r. K r plus k1r gonna be 0. That's right. So now let us go to the example. Okay, let us go to the example. I am gonna do 2 examples because this is very important, guys. Example by Matlab. Suppose the open loop transfer function of the system is this: 1 over s plus 2 s plus 3. First of all, this system is third order system because the highest order of this is s cubed. That's right. So you're gonna have 3 state variables: x1, x2, x3, right? And now your boss says, okay, design a controller that gives me a pair of complex conjugate poles, -2 plus minus j root square of 3 and s3 minus 10. The first question I taught you, why you want to have the real part of the s3 becomes 5 times of s1 and s2, because this is gonna vanish soon and gonna be has no effect on the dynamics of the system. And you have pair of complex conjugate poles because your boss wants to have under actuated under dam system. That's right. For what? Design such a controller that it follows R as a unit step. Okay. So first let me plot this block diagram, guys. This problem. I'm just recording. Yeah. So this is the problem block diagram. This is R, unit step. I want to follow it. And I'm gonna here put plus plus. And this is the open loop transfer function that problem provides. S plus 2 in S plus 3, right? And this is U going to the system that we are designing this, you as a control engineer. And this is Y, and this go back here. That's right. And so this is your plant. You see that Y over U based on the problem is this. This is undergraduate control. You had to know it. Okay. So the first things that I taught you is this. What you're gonna say? You're gonna say denominator and numerator. That's right. Numerator of this system. Denominator of this system. Look at here. S in S plus 2. I'm going very trivial step by step. This is denominator. Gonna be S in S square plus 5S plus 6. So at the end gonna be S cube plus 5S square plus 6S plus 0. So denominator of the system, as I taught you in the Matlab, gonna be 1, 5, 6, and 0. Sorry. So based on the third order system, denominator of the order of this is 0. So it's gonna be 0, 0, 0, only constant number 1. Here we go, as we're gonna type in Matlab right now. Okay, so by doing that, as I taught you, you can type this command and say, you can say ABCD of transfer function to state space of num and then. This gives you ABCD. Let us do that together, huh? Because we are designing controller for the third order system. Before going ahead, guys, this system, listen to me very carefully. I'm just changing the color. This system, let me change the color to this to be visible. This system has one integrated in open loop transfer function, 1 over S. Because if you remember from undergraduate control, a Laplace of integration is 1 over S. When I say integrator from undergraduate control is 1 over S. So this system has an integrator. I'm emphasizing has an integrator in open loop transfer function. So that's why you can design this. You can use this state feedback control law. So when it doesn't have, it has another formula I'm going to teach you. So this is for the has an integrator, okay? And non-zero because it's a unit step from undergraduate control. This is unit step. You want to follow this, okay? So now going to the Matlab. Okay, sure. Now, what was the num? The num was 1, 5, sorry, num was 0, 0, 0, and 1, and the then was 1, 5, 6, and 0. Here we go, right? So now I'm gonna say A, B, C, D in a state space is equal to transfer function to state of none and then. Here we go. because the system is third order system, you're gonna have 3 by 3a, a 3 by 1b, 1 by 3c, and d is 0. That's right. So you see, Matlab gives you. So let me write it down here. So let me double check. What the hell is this? Okay, this is -5, -6, 0, 1, 0, 0, 1, 0, 1. B is 1, 0, 0, 0, 0, 1. So this is the Matlab that gives you. Okay. So here we go. So Matlab gives me this x.1, x.2, and x.3 is equal to, I have it, -5, -6, 0. Yeah. So 1, 0, 0, 0, 1, 0 in state variables, x2, x3, plus bu. It's b because single input, single output system. That's right. B is 1, 0, 0. This is 1, 0, 0. So this is your A, this is your B. So y is equal to cx. C is, as Matlab says, is 0, 0, 1, 0, 0, 1 in, again, your state variables, x1, x2, x3, plus 0, d. D is 0. So this is your C vector matrix for CISO system. Understand? No? So if you don't want to do that, this is Matlab approach. You can have by your hand. This is very comprehensive problem, guys. I want that you learn very deeply. Okay. So you're gonna say, why is it stopping? Hold on. Let me fix it. Okay, so now by hand. By hand is because your transfer function is like this, is 1 over s plus 1 in s plus, s plus 2 in s plus 3. You can say, see, you can say x1 is y and the x2 is y. That, remember that we were doing. So having by time derivative, you're gonna have x dot 1 gonna be x dot 1 gonna be y dot is x2, right? Now x dot 2 gonna be y double dot. I'm gonna name it as x3 because it's third order system. And now x dot 3 is y triple dot. And what is y triple dot? We have to calculate from here, guys. This is by hand. We know in Matlab. Look at here. If you multiply the both sides, you're gonna get this: ys cube plus y 5 s square plus y 6s is equal to u. Remember, if you apply the Laplace inverse from the graduate control, this gonna gives you y triple dot in time domain plus 5 y double dot in time domain plus 6 y dot is equal to u. But what we want to find, y triple dot. So you're gonna have y triple dot is equal to u minus 5 y double dot minus 6 y dot. So what you get is this: u minus 5 double dot y double dot is how much? Is how much? Y double dot is x3. Look at here. Y double dot is x3. 5 x3. What is y dot? Is x2 minus 6 x2. I'm gonna put it here: u minus 5 x minus 6 x2. So your state space equations becomes like this by hand. X dot 1, X dot 2, and X dot 3 gonna be, here we go, X1, X2, X3. Look at the first line, only X2 is here, so 0, 1, 0. Only X3 is here, 0, 0, 1. And here for the state variable, it's gonna be here. There's no X1, 0, X2 is minus 6, minus 5, plus BU. There's no U here, 0, no U here, 0, only U is here, this. Bingo, we got that. Understood? So guys, by hand, this is your A. Pay attention very carefully. This is your B. By Matlab, as you saw, this is your A. Here we go. See? This is your A. Let me write it down. Matlab gives me minus 5, minus 6, 0, 1, 0, 0, 0, 1, 0, and this is your B. B is 1, 0, 0. 1, 0, 0. So do you see any relation between your hand-driven A and the Matlab A? Do you see? So if you don't see, let me now, based on whatever I have, you boss wants from rule, let me find the gain matrix, because we're gonna design this controller at the end of the day. This gain matrix, this K first. How we do that? Let me go with you. Your boss says, come on. Your boss says, I want to have these poles, desirable poles, eigenvalues of the system. What are those? As I taught in the previous class, J is minus 2 plus J root the square of 3 minus 2 minus J root the square of 3. At the end is minus 10. As I taught you have to type in Matlab. And then gain, as I taught you, is going to be acre or place your A matrix, B matrix, and J matrix. Okay, let us calculate that in Matlab. So, as I taught you for the state feedback with the going back to the origin, I'm going to do in Matlab right now with you. In file, why I'm doing in file? Because to save it, I'm going to say A is based on what we derive by hand, 0, 1, 0. The next line is 0, 0, 1. Next line is 0, minus 6, minus 5. That's right. And your B is 0, 0, 1. Here we go. Now, gain matrix is going to be acre. A, B, oh I forgot to put J. These are poles eigenvalues. It is minus 2 minus I multiplied by the SQRT of 3. Minus 2 plus J multiplied by, or I and J in Matlab has the same meaning. A complex number, imaginary number. SQRT of 3, and then minus 10. Here we go. So acre, acre is wrong. Acre, A, B, and J. So I'm gonna save it in ME6 196. So you're gonna have acre of third order system. So if I calculate, let me delete this to avoid confusion with this. So if I run this, Here we go. Oh, what's wrong? IQ. Oh, stupid mistake. This is color. Okay, so it's gonna give you 70, 41, 9, guys. So this gonna give you this gain matrix. For this problem, this gonna be 70. Bear with me because I have a point. 49, 49, and 9. Oh, 70, 41, 9, 41. Why it is 70, 41, 41, 9. Here we go. Understand? So this is your gain matrix. But based on whatever I taught you, here, where is it go? Your U is minus kx, and the first element multiplied by R, unit step. Understand? So R is based on, you know, from undergraduate control, unit step is 1, whatever. Okay, so now let me develop the code function. Dx is equal to, the name must be exactly like this. Now you know it. Ackermann third order time and x state variables, right? Dx is equal to zeros. I have 3 state variables, space for them, 3 and 1, right? Then I have a, b, j, and the k. I'm just putting a space here. Please type with me and try it, okay? Now I say the u is minus k, as I taught you today, because system has integrator. Again, the system has integrator, guys. System has integrator, okay? So, and in k, and multiplied by a k in x, which is x1, x2, and x3, plus k1. So k1 of this was 70, but you don't need to type it. Be smart. You say k 1 and 1, first element, first row. That's right. Multiplied by, you can now define R, the desirable input. Say here, say unit step 1. Bear with me in R. Now typing the equation. Dx1 is equal to this is for the hand driven. And d1 is equal to x2. dx2 is equal to x3. That's right, as you have in notes. Here we go. See, this is that with x2, x3, and 0, minus 5, minus 6. That's right. Here we go. Please. X3, and dx3 is how much? Minus 6 x2, as we did, minus 5 in, I'm typing like this because I'm teaching you. I don't write the equations like this typically. So let me double check. See, plus u, we just designed u. This is that we designed for system having an integrator and non-zero reference input. Here we go. Understand? Here we go. Now I have to solve this differential equation by applying the control input that we designed to see how it works. So it's going to be t and y output. Going to be again ODE 45 at Ackermann third order file, go and call it, between 0 and 0.1 to 10 seconds. Third order system, you have to have 3 state initial conditions, 0, 0 and 0, because we're going to put it there. So we're going to push it to 1 and 1. Understand? So that's it. Understand? And now if I say figure 1 plot, I taught you this plot time, total time, and the x1, which is y, 1, and blue line, and the line width is 2, and grid for me. Oh, okay, I'm gonna fix later. Fix later. X label is time, second, and y label is what? Y label is y of the system based on your transfer function. Here we go. Let me debug it first. Run it by debugging. Oh, whoops. System based on your bus requirements has a pair of complex conjugate poles at -2 plus minus I root square of 3. That's why showing this transient under damp response, and then goes to the 1. Understand? So we are fine. So if I wanna plot it for 3 seconds to make it more visible, there we go. See? And then goes to 1, to unit step. Understand? So if I change it, I say for a system, you want to push it to 45. 45. Here we go. Goes to 45. Here we go. You don't have to just stick there. Now suppose, just assume, I'm emphasizing, assume this is your car equation of the motion. I'm not saying that it is. Suppose this. So you want to put the cruise of your car, and they're gonna, you know what, fix speed as 76, I say, mile per hour. Mile per hour. Here we go. Let me see if it does. Oh, it does. It's 75. Sorry, 65. So if I increase this to 5, to specifically shows to you. See, 65. So, but in the control problems, you want to also see the U. So it's enough that you put inside here U as output of the system, and now this has already 3. That's right, y1, y2, y3, or x1, x2, x3. Fourth line, look at here. I'm just showing here, guys. This time. X1, X2, X3, hold on guys. Do I forget something? Hold on guys. Okay, but before going there, I had another thing in my mind just because I forgot to, I wanted to teach you. Okay, so now we saw that after having integrator, guys, okay, what are these? So I think after having integrator, okay, so we go to the desired set point that we wanted to push our system. So, and I taught you guys that system has integrator. Okay, system has integrator. First of all, you saw that by Matlab inverting Matlab from state transfer function to state space, our A was this. Look at here, guys. Our A was this. Was different from our hand-driven one. 0, 1, 0, 0, 1, and 0, minus 5, minus 6, and 0. See? So let us do that. I want to see what's the difference between those answers. So gonna be minus 5, minus 5, minus 6, and 0, and 1 flipping this 0, 0, and 0, 1, 0. This is based on what Matlab gave us, this state space. That's right, right, as I did in the beginning of this class. And B was 1, 0, 0, was like this. That's right. Now again, the J is the same. First of all, I want to see what is let me do it outside of the here. What is the gain that we get? Look at here, guys. Let us see. Is 941.70. Okay, so with the gain that we got by our hand-driven was how much? Did I write it? Yeah. It's flip of that. That's right. It's flip of that. See, it's flipping. So it doesn't make change that you are doing by Matlab, you're doing by hand. Okay. So if you do that even, okay, now you're gonna have so you have to change the equation of the motion here based on whatever you have. Minus 5x1 gonna be based on, if you do that, please do it at home. Minus 6x2, and there's no this. Oh, I have to change it. It's gonna be like this. Look at here, guys. It's gonna be like this. You have to change everything here. Minus 5x1, minus 6x2, and there's no x3, plus u, right? Your x dot 2 gonna be x2, and your x dot 3 gonna be, so gonna be x1, and your x dot 3 gonna be x2. Here we go. That's right. Look at here, guys. I just wrote this here based on what we did by Matlab. Here, this is the Matlab. That's right. This is the Matlab version. Minus 5, minus 6, minus 6, x2, minus 5, x1, u, because u is here, 1. X dot 2 is x1, x dot 3 is x2, right? Now if I plot it, let me close this. So what do you expect to see? Oh, because everything is flipped. Here you have to plot x3 to give you the reference input. You know what I mean? You know what I mean? So this is another issue that you have to know about that. Now you have to, if you say here is xy2, that's right. Here is this, and now, oh, I have to change this. Also, it's gonna want 3 because you flip everything. So if you flip everything, so you're gonna have 65 again. Understand? So the Matlab version that you are giving you have to flip everything. Okay. So this is one lesson taken. That's why data driven that you have to do that is much better for you. Understand? So that's it. Now let me go back to the previous version that we didn't change, and we did everything based on our date model driven. And here is 1. Here we go. Okay, so now we know how to design controllers for the non-zero integrator. Now my question is that go at home. Okay, let me go to this.